Hi. In this video we're going to look at adding vectors together in polar form. We're also going to look at the scalar multiplication of vectors in polar form. So we'll start there because that process is very, very quick. So when we scale a vector, the direction of the vector doesn't change, only the magnitude changes. So up here we've got two vectors. We've got our A vector, magnitude 15, direction 35 degrees from the x-axis. If I wanted to find 2A, so if I wanted to scale and multiply that, all I'm doing is doubling the magnitude and keeping the angle the same. So quite straightforward process for scalar multiplication of vectors in polar form. Addition of vectors is a little bit more involved. So let's have a look at that. Whenever we have something set up this way, I should do this in brackets like this. Whenever we have things set up this way, it's easiest just to draw a diagram. So what I'm going to do is we've got 35 degrees and 15 length. I'm going to make the diagram quite big so we can see it. Then we've got 10 length and along that x-axis. So not quite as long as something like this. If we're adding together the vectors, we want to get this resultant vector here. Okay. So we have this triangle, let's label it. We know this is 15. We know this angle is 35 degrees. And that's the big angle, not the internal angle in the triangle. It's going the whole way down to the axis. We've got 10 as that length. This is our magnitude of A. This is the magnitude of B. And if we let this length be C, we want to determine what the magnitude is. We also need the angle. We need to work out this as well. But let's start with the magnitude. So there are a few more things that we can do to fill in this triangle. We know that this is 35 degrees, and using our Z rule, we also know that this part here is 35 degrees. So if we call this theta, because of our Z rule, if that's 35 degrees, we can find out what this internal angle is, if we call that theta 1. We get 145 degrees. Okay, so we want to find out this length. We know 3 lengths of our triangle. We know 2 lengths of our triangle, and we know this angle. So there's a formula that has 3 lengths and an angle in it. That's called the cosine rule. So in that formula, we have one unknown, which is a length. We have 2 lengths and an angle, so we have the other 3 things. So we can use that to solve. So cosine rule, the way I remember it is it's Pythagoras equals a squared plus b squared with a slight modification. So we got 15. Our angle C is directly across from our side length C. 225 plus 100 is 325 minus 300 cos C. Our C is 145 degrees. That equals 570.75. Now a common error is to leave it like this, but if I look at my picture, it's obvious that this length is not 570. This is actually c squared. So c is the positive square root. And we get 23.89. So that represents our magnitude of the vector c. Now we need to work out what our angle is. So our angle is referring to this green guy down here. Now, we can work out that green guy because we know that's exactly the same as this angle here because of the Z rule. So if we can work out this angle, then we know what our direction of the vector is. So this angle, we've got matching sides. So we have this side and this angle. We have this side and we don't know this angle. Now, the way that we can use those four quantities together is with the sine rule. So we've got our unknown, which is up here. So I'm going to put it on the top of my equation. Let's call it alpha on 15. On 23.89. And again, it's good if you can use the exact value for that. We've got sine alpha, so sine alpha equals sine 145 times 15. Alpha equals the inverse sine of that. And I put that into the calculator, what do we get? Oops. Bracket. 21.11. Okay, and that's our angle alpha, which is up here. Whoops, which is up here. So to get our angle here, let's call it alpha 1. That's just equal to alpha because of the Z rule, but it's good to communicate that. Alpha 1 equals alpha because of our Z rule. So when we want to state what our final vector is, C, we can say C equals 23.89. And we've got our final vector in polar form. Okay, so I'm going to include a slightly different problem here to show you how it will work. So here we've got the same first vector as the previous question, but our second vector has an angle of 10 degrees. A little bit different. In the previous question, we had an angle of 0 degrees. This will make the working a slightly bit different, but pretty much the same. So let's have a look through the steps I've done so far. We've drawn our diagram. We've got 15 magnitude and 35 degree angle. We've got our second vector, 10 magnitude, 10 degree angle. We can work out that this angle here is the same as this due to the Z rule, that doesn't change. We can work out our internal angle here because 35 degrees plus theta, but minus this little 10 is going to equal 180 degrees. So I've written that out here. We can then solve for theta and we get 155 degrees, which is 10 more than we had in the previous question. Makes sense because we've had this little 10 degrees in here. We can then work out our side length. We have 2 lengths and an angle, so we can work out our third side length using cosine rule. I've done that up here. Now when we're working out the angle or the direction of this red vector, of our E vector, we can't use the same method as we did last time because this line, this axis here, is not parallel to this vector up here, so I can't use the Z rule. However, I can still find out what this angle is here using the sine rule. So let's do that. Equals equals, what have we got, sine 155? Equals and we get our alpha equaling 15.04 degrees. So that's this angle in here. Now we need to somehow relate that angle back to our angle all the way down here. If we know alpha and we know theta, we can work out what this angle in here is. Let's call it beta. We've got theta plus alpha plus beta equals 180. So we can work out what beta is equal to. That's just going to be 180 minus our 15 and minus 155. We get 9.96 degrees. If we know beta and we know this bigger angle here is 35, we can work out our small angle down there. So we've got, therefore, let's call it, what do I have left? Let's call it gamma. Gamma equals 35 minus beta, which is 25.03 degrees. And we can write out what our vector is now. So E vector and we've got our vector in polar form. So slight different calculations in terms of the angles if we don't have a 0 degree up here. Let's go back to the video. Now, fairly involved process using the cosine and the sine rule. You can also do this by converting your original vectors in polar form to component form and then add them and then convert back. So you can finish the video here or you can keep watching to see what it would look like in that respect. So we've got 15 and 35 degrees. I'll rewrite it out down here. And B was 10 and 0. So A in component form B in component form is just 10 and 0 because it's along the x-axis. So if I'm doing A plus B, I've got 15 cos. Let's input what that's equal to. We've got 8.60. Now, to convert that to polar form, we need to find the magnitude and the direction. So magnitude, let's call that C. $23.89. That should be the same as what we had up here. Yep, it's the same, so 23.89. Let's get our angle. So what do we have? We've got 22.29 across, 8 up. Let's call this beta so we don't have the same variable equaling different things. And we get 21.10, which is slightly off because we've rounded these, but it's 0.01 off, but the methodology works. So you can see that this method here of converting to component form is a little bit quicker to do, but you do need to know both methods. Adding in polar form involves cosine rule and sine rule. So thanks for watching the video. I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.